Hello and welcome back to the Hello and welcome back once again to the show. My name's Relevant. This is Do All the Things. On today's episode, part 2 of the Train Box Upgrade. Today we're going to shoehorn the new power components into it to get more current. Stay tuned. So where we last left off, I replaced the output module in this thing with one that has a relay on it. And I dug up the part numbers for this iteration. It's black in the photos and it looks like I bought the last one. Oh my, RTE 24012, 12 volt, 8 amp relay. And oh wow, it made a huge difference. Like literally, it's ridiculous just how much of a bottleneck the Mosfet drivers I was using as a hacked H-bridge before were, they were brutal. Not only is this thing more responsive now, like in the low end, I can get like a more subtle, sturdy goer there. I get more voltage output, more speed, and even more current. I thought I was gonna have to upgrade these inductors to get the more current, but I've measured up to 2.5 amps easily out of this thing. Sky's the limit now a bit. It turns out I was wrong about the inductor. It might have some sort of voltage drop when it gets saturated, but it was nowhere near anywhere close to what I thought it was gonna be. Even though I only have a 1.5 amp inductor in here, it's passing current, and I'm surprised I haven't blown the diode. The diode's only rated for 2 amps. But I guess being on a duty cycle, tick, 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 on and off, is kind of saving it from getting fried. It's not completely continuous. And really, I think we have some sort of weird averaging going on here. Whereas more than 2 amps can force its way through the inductor, but during the Mosfet off cycle, the inductor can't really generate more than what it's rated for, an amp and a half. So we might not have as much current on the off cycle as we do the on cycle, and that could also be why the diode's not getting fried, because it's only being asked 1.5 amps. So I did this first part of the mod on a Wednesday. It is a Monday now. I've been playing with this thing for a couple days now. It's almost maybe debatably a bit dangerous because I did have one problem that I had to solve. And that was short circuits could be more of a disaster now. Those Mosfet drivers were acting as current limiting, preventing short circuits from completely just frying this thing out. That might not be the case now. So basically what happened was I decided to do a test. I took a screwdriver and I put it briefly across the tracks to simulate a dead short, and I got a nice healthy spark, and then when I pulled the screwdriver off, I had a runaway train. Okay, so let's see if we can explain what happened here. So basically, when I short-circuited this, it damaged the Mosfet. And it damaged it in such a way that we lost our gate isolation. You see, Mosfets are easy to work with because you can pretty much connect their gate to full supply voltage and they just work. They don't have any current runaway. Unlike a transistor, where the base of a transistor isn't as isolated, if we connect it to full supply voltage, it consumes too much current. It'll actually try to draw load from it. So we need a current limiting resistor. MOSFETs generally, we don't necessarily need that. However, when the MOSFET got damaged and we lost our gate isolation, it started drawing way too much current from the output of the MOSFET driver, damaging the MOSFET driver too, specifically its ability to put out a high signal to turn it off. So now the MOSFET with no control basically sent full battery power 18 volts to the track, and I had a runaway train. Now the MOSFET I was initially using is the FQU11P.Ep.6. There's his part number. Oh, this guy's also out of stock. Yeah, I hear there's a shortage right now. But anyway, I kind of liked this guy, but it's only rated for 9.4 amps, which is more than enough for the application. And one of the reasons why I chose this for the application is because it had good specifications. It has a fast switching speed, a very low on resistance, and a very low input capacitance. These are features that are good when you're trying to build a very efficient PWM. Now, when I replaced it, I did have another one like it in stock, but I chose to go with the Alpha Omega 21357. This is a cheap Swiss Army MOSFET that I keep in stock, P channel, and it's actually rated for 23 amps. So I'm I'm hoping that with a 23 amp rating, if I do get a dead short circuit, I'm not gonna have as catastrophic a failure. It's gonna be able to handle that that little punch to the face a little bit better. The only thing is it's generating a little bit more heat now because it doesn't have as fast switching. It doesn't have as low input capacitance. It shouldn't be that bad. Turn on time 12, 18, 125, 66 compared to 6.5, 40, 45, 45. So yeah, the alpha omega is definitely slower. Where's our input capacitance? 450 to 550 PF. What do we got here? Oh, 2380 PF. On resistance, RDS on. Where is it? Anywhere from 6 to 9 milliohms. What about the FQU? 150 milliohms. It looks like it has a higher on resistance. Okay, but if you have been paying attention, you're gonna notice the FQU has a VGS of negative 10 volts, whereas the alpha omega has a 4.5 volt rating. Yeah, the alpha omega, one of the reasons why I call it Swiss Army is because it'll actually handle a low level logic input signal. You might not know this, but MOSFETs, you know, if you want to run them quick for switching applications, you can't just hit them with a low level logic signal. That's why we have the MOSFET drivers you gotta drive them with roughly the same amount of voltage that you're running at, or at least 10 volts or more. Either way, we've changed out this MOSFET and yeah, this thing's working nice now, but what I wanna do now is continue on with this modification, and we are going to do the rework to the power supply module, upgrading the inductor. Here's the existing power supply module. Our existing inductor is a Murata 14105116C. Again, 1000 microhenry, 1.5 volt rated. Schottky diode, just a SR, what does that say? SR206, 60 volt 2 amp. So we gotta remove these, and I'm gonna be putting on this guy and this guy. And this guy is a Bourne's 2300 LL102 VRC, also 1000 millihenries with 3.5 amps. And then our new Schottky diode, higher current, as mentioned, is gonna be 20 amps. Dug up the part number again, SMC MBRF 2045. Now, I don't necessarily recommend either of these components. I've never used them before. This is gonna be a test. These guys have to draw the label on it so I know right quick. And I do believe I have a layout ready to go. Something like this, semi-incomplete. So I have the screw point labeled, and I have roughly where I want to put the diode, but I don't have my input and output for the inductor labeled here because I'm not 100% sure where I'm gonna put it now. It's a bit larger. I assumed I would get to stick it somewhere on there like this, but we have the problem that there's a big chunky screw here. I kind of designed this in such a way that the inductor would be bolted down. And oh yeah, undoing my work here is gonna be fun. See, the only problem with perf board, and you get right into it, you weave this tapestry of componentry together, and then sometimes good luck taking it apart again after. Fortunately, I didn't do that with the MOSFET because the MOSFET doesn't really have the right kind of leads. They just kind of poked through, and I wrapped the other leads around them. So changing out that MOSFET was relatively painless. Okay, let's do some surgery. I'm seeing some promise here. What's going on here, sir? Oh, I weaved that right under. I don't want to waste this inductor, so I want to recover as much of the lead as I can. Okay, that one went well. What about this one? Ooh, where are we hiding this? Oh, not the way I thought it was. Okay, I think this big lead here is for the diode. Might as well pull that off. Okay, I think I kind of got it here. Now, unfortunately, we damage some of the pads on the perf board when we do this sometimes. They're kind of one-time use only, you know? Okay, inductor salvaged. Oh boy, look at the teeny tiny leads compared to this one. Like, just the leads look chunkier. I got that diode. I did get that diode out of there. Ugh. Diode I'm not too worried about because it's a much cheaper component. But I did manage to get it mostly out, so. It will live to diode another day. Diode another day. Huh. Some sort of nerdy James Bond flick. Diode another day. Oh boy, where are we gonna put this thing, man? It's like, how are we gonna get this mounted well enough that we can still get the bolt in there? Well, there's a way, bud. We just have to first figure out where this thing's gonna go, because I'm gonna put this guy on, and half of that has to do with sandwiching it underneath here so it can get cooled by the chassis. Even though I'm starting to wonder if this thing's actually gonna generate that much heat, because that little 2 amp, it was running pretty hard. It didn't generate much heat. Okay, so part of the plan is to go to a smaller 1/4 inch standoff and then fold the diode over onto that standoff so that it would be like something like this. Oh, it doesn't look like a 632 screw wants to go through this hole. I'm gonna have to widen that hole. Fortunately, there's nothing important there. But if I get rid of the insulation, that might not work now. Uh-oh. Okay, well, there goes my plan for diode mounting. Once again, we go full circle back to the concept that I don't think that thing's gonna generate enough heat to overheat. Perhaps we should find out. Perhaps I should mount it in there normally. Perhaps I should try drilling a bigger hole through this first. And then if we damage it or lose our insulation, then we'll mount it normally. Deeply, we need this 964 hole in here. All right, how's it look? Yeah, it looks like we still have isolation. Poke a quick floof through there, dust the wets. Yeah, we might be okay. Back to a regularly scheduled program. All right, it fits, so it sits. We have to determine optimal placement for it now. I think we have to bend this maybe like that. Oh. Okay, that should be about right there. Let's just put a nut on the other side to hold her firm. Okay, a fold over like that, and it will heat sink against the chassis. So I'm gonna tempo tack this diode on there because we need to do some fitting before we can actually put this all together. And it definitely shortened the length of this guy because this is quite the long bolt. This one too is gonna change because we need to get the same size standoff for it now. And we need some spacer about the same width as that diode. What about this nut that came? Oh, that nut's gonna be perfect. So we're gonna need a much shorter screw. I think the shortest stick I got still gonna work as a 1 inch. And we'll put our spacer nut into place. 1/4 inch standoff. Now to fit this kitten. Oh, this is gonna be tricky, bud. Oh, this might be more trouble than it's worth. We gotta get this guy to stay in place. Actually, there is an easy solution to that. These standoff dealies are just like plated brass, buds. So with it, fastened to the board, we should just be able to get a little bit of solder tacking it into place once we know where it's gonna sit. Oh yeah, solder sticks to it right nice, bud. We just need to get enough heat on it. Okay, I think I got it in there good enough now. Whew, still hot. So now fold that over. Now we should be able to sandwich this in there and get a screw through this hole. Ah, yeah. Now we have a diode to chassis sandwich and a little dingle here sticking out a bit too much than we want to. And oh, look at all the solder scabs. Oh boy. I need to flatten this out now. Okay. I didn't show that process, but so let us fasten a nut on there. That is what we have to work with. So now I gotta fit some way, somehow, an inductor over this. It's funny, there's almost like a whole bunch of room beside it over here. But that's part of the ground bus. Or is it? Debatably, for what I have going on here, this is a bit too close together. Okay, I think I got it figured out. If I put it here, I should have enough room to clear the kep nut. Just enough room to clear the kep nut. And wiring wise, I should clear the routing. I should put the inductor connections here and here, which is somewhat convenient because it means we just couple that. We need to couple with that line, then we have a straight shot to the output. Okay, I think we have a plan now. Let's get it done. And that debatably means securing down this diode, even though that's gonna make it tricky to route the lines. All the lines which are doubled up. Get her done. Fold that over. All right, let's fold this line over. And then we need that to come down here to that diode hole. This looks messy. I almost wonder if we could just wrap this around. Like, we don't even need to really put it through a hole. And yes, that's gonna work. We've wrapped the diode lead around, so it's gonna come in contact with the power bus. So that should work. Now we just have to ground this pin, which I think I can do after the fact. Okay, so let's get one side of the inductor soldered on here. Let's sit the diode in place and fasten it down for a brief moment. Simulating correct spacing. Oh, okay. One diode leg Secure the second. All right, the diode's on there now. Just a connection to the negative bus there, and then this fold over goes under to half of the inductor. Oh, is there enough slack here that I just fold that down? Oh, it's just not gonna make contact with that inductor. Okay, we just have to straight shut that across. Do that by weaving in some of this line. Now, is one weave gonna be enough? Because all these load bearing sections I've doubled up. We got a thick wire coming all the way here. Double wire here is just that one little spot there. Question is, can we get enough solder on that spot to bridge that gap? Yeah, you know what? I think it's gonna be okay. We should have a good current conductivity across this beam. I have to double check all our scabby sections where we cut and pasted connections. Oh, my inductor's not sitting nice. Of course. Watch, I'm not gonna be able to get a kep nut in there anymore. That's just wonderful. Unless we just slide it over a bit. Okay, I think we're gonna be good. Yeah, all right. It's not slacked the way I had planned. Need to be a little bit more mindful with my lead spacing. All right, so these connections here still look good, even though they're a bit scabby. One of those is just a resistor. I have a 10K resistor here. It's just for an exhaust vent, so that when you turn it off, that should let power drain out of the system. And then 10U output stabilization. Not even sure if that's appropriate. We have this section here where the diode used to connect. There's a bridge point between two ground buses. Yeah, I need to fix on this. Now, I just want to position this loop nicely there and then get these existing leads into place. All right, rebuilt that weave, tack it all down. That should be it. This should be ready to install now. In theory, assuming I didn't get that diode backwards. I don't think I did. Let's see if we can't get it shoehorned back into the enclosure. And this guy's coming loose already. Those pads are not on there well, so hopefully I can get it to just stay in place long enough to get this into place. We're going to put the slightest whiff of thermal glue on here. Oh, why is that so runny? Oh, that's sexy. Yeah, should do. Ugh, got it all over me. All right, aha, it bit. All right, where's all our kep nuts, bud? Let's see if I can't get one right in here. A little bit tight up against that inductor. But we got her. Fortunately, this isn't a device that suffers a lot of vibrations, so. And then, yeah, it's just the inductor bulges here. Once we got it flat down in there, she's gotta be good. Oh yeah, 'tis mounted. Now I also wanted to maybe change out the Zener diode. I used to do a 12 volt with the idea that this circuit had about 1 point something volts drop and I got 14 volts, but no, I had to raise that up. And if you could see in there, I actually have two of them now. I got two Zeners in series, a 9.1 and a 5.1 to make 14.2. And then I get about 1 volt of deviation. So I get 15.2, 15.3 volts out of this now. I was thinking of just straight up sticking a 15 volt in there, the same way the old one was. Get up to 16 volts. We'll see, we'll see. 15's pretty good for now. As much as I want more speed, that's not the way to get it. This should be ready now. Now, in a previous episode, as mentioned, I'm running it off power tool batteries. And I got a nice upgraded 18 gauge wire. That is part number 10-01776 Tensity 18 gauge. It's behaving suspiciously. Oh, it switched. That's what that 10K is for. So let's do an initial test here. Oh yeah. Oh, it's working. Now we have to test current output. All right, so we've attached all sorts of metering to this. And we got some old power bulbs here. 12 volt, this is 12 volts, 18 watts. So 18 watts divided by 12 volts, that's 1.5 amps. It should have no problem running this bulb now. All right, so let's have you 740 milliamps. Bringing it up, 1 amp, no problem. 10 volts, 2.1, we're already overshooting. Let's bring it up to 12. Carefully now, carefully. Don't want to overvolt the bulb too much. These guys pop right fast in a hurry, even though it should handle up to 14 volts. It's not the finest adjustment on this, but there we have 12.5 volts, 1.4 amps. A little bit of warmth from our inductor. Diode, not so much. That Mosfet, can't tell, it's buried in there. So, that worked. This one's 12 volt, 35 watts. That's 2.9 amps, so that should give us a better test. That should have been over the threshold for before. So let's bring her up. 6, 7, 8, 9. Oh, 2.4. 12.6. 2.6 amps. So a little bit under. Might have a bit of bottleneck on these crappy little wires. Actually, let's stick the meter on the bulb itself and see how much voltage it's actually getting. Yeah, it's pretty good. I think I feel some warm from the inductor, the diode. A little bit of warm from the inductor. MOSFET again, hard to tell. Oh, we need to pump these numbers up. This is a 28 volt, 150 watt air taxiing light. We're not gonna be able to get this bright. There's not enough voltage here, but we should be able to chonk enough voltage into this thing to get up to 3 amp output or 3.5 amps. So, okay, 2 amps. It's just barely, like, it's on. Here, I'll turn it around. That's what 2 amps gets us on this bulb. Oh, I can feel heat off of it already, just radiating. It's at 4 volts. Now let's bring her up to 3. There's 3 amps, 9 volts. And at 12 volts, 3.5 amps. That's our target. Inductor's a little warm. Oh, that MOSFET's getting hot. Geez, if we actually run this at 3.5 volts, we might have to do something about that MOSFET heat sinking wise. Oh, it's a nice little heater. 12 volts, 3.51. 12.42 times 3.51. We're getting 43 watts out of this thing already. That's, oh, I feel just a slight, just to say. I almost want to see how far this can go. Huh. Oh, wow. So right now she's cranked 3.8 volts output at 14.7 volts. So we do have some voltage drop. And there's gonna be, like, the governor circuit's kicking in right now, so it's PWMing. What is this? What is this? 14.75 times 3.83. 56 watts. Heat checks. Diode definitely gets warm. It's barely though, but like the back of this panel's starting to warm. So the heat sinking is working. We might have to do something similar with the MOSFET. We'll see, because I highly doubt I'm gonna blow this 20 amp MOSFET running trains. Ho ho ho. Now we need to go and actually test it with the trains themselves. All right, so here we are. I've stacked up a very similar 60 car consist. It is almost identical. I just changed the order a bit to make it more stable. And so now let us get it rolling. Now the first thing you notice is much better control. The slow speed. Oh yeah, it's a heck of a lot easier to start slow and then get it rolling. Which is what we gotta do. We can't put too much torque on right away or this consist will fall apart. So we'll gradually get it up to speed. Oh, we're way different already, bud. So we were at about 13.7 volts before, 1.4 amps. So right now, I'm batting 13.9 at 1.43 amps on the amp meter, and I'm not maxed out yet. I'm at this o'clock. That means we got more. This is 8 right here. 15.28 volts. We are hitting max. And we're getting between it's all over the place, but we're averaging 1.5 amps. So already, we're all the way there. Now we just need to time it. And go. The time to beat is 53.33 seconds. That's what it took it before to get through. Hey. And stop. 46.11. So that's shaving off 7 seconds. It's 7 seconds faster. So we're not seeing huge gains in speed, but we're definitely seeing gains in performance. But it's great that I can bring it down to where it was before without maxing out the dial. That's part of the goal here. Our inductor isn't even coming close to get warm. I don't really feel warmth from the diode either. MOSFET, a little bit warmth there. And bringing it to a stop. All right, so these guys I've found with maximum tractive effort consume about 750 milliamps of current. What that means is, you know, they can only pull so much because they're limited by their weight. If, as HO scale implies, and these were to scale by weight, they'd still weigh 2,000 pounds at this size, but they don't. So one of these guys pulling as many cars as it can without slipping its wheels, only 750 milliamps. It could consume more if it had more weight, but it can't. So we want to throw a little bit more current at the situation. So what we're gonna do is we're gonna stack up a trio of black motors. My little 4-axle GP engines, they got black motors in them. And even though they're not gonna have as much tractive effort, 3 of them still should pull this. There is a lot of weight in the old F7 Super Drives. So this is a B unit, also with the black motor. And then we'll top that off with my chassis. I put a little bit of extra weight into it, but yeah, that's 3 engines with black motors. That should start sucking back the current. Oh, maybe they don't have enough tractive effort. Oh, they do now that they all synchronized. Problem with the black motors is they're slower starters, so they might not all kick in at the same time as you gradually go up. Huh, we're at 1.6 amps already. I see current jumps every time I turn up the knob a bit, and then the amperage settles down as the consist comes up to speed. I can't quite break 2 amps. I don't know if you can see that, but I'm hovering 1.9. Oh, it just dipped down as it got farther away. It'll go up as it gets closer. Roughly almost 2 amps at 12.5 volts. And this is probably at about the speed the other train was going at. We got more because these are black motors. The acceleration is there because the power supply doesn't hesitate. We're 2.1 amps at 14.1 volts, and we still have more. We're at 8 now, 15.2 volts, also 2.1 amps. I guess we're maxed out. Black motors are absolute rippers. The low speed control is just so much better now because the current can actually get to the motors. Right now we're 1.3 amps at 3.8 volts. That was unheard of before. So if you recall last time when I fired up the 2 black motors with my passenger consist on the other track, when I threw on the second engine, it went slower instead of faster. Let's compare that this time with the one F7 Super Drive and the dummy F7A out front. Let's bring it up to speed. Now this thing has a bunch of LED lighting too, so more than just the engines consuming. Oh jeez! I forgot to switch the track over. Technical difficulties, be right back. All right, back on track. This is half speed, which was probably full speed before with the other engines. All right, let's bring her up to temperature now. Max 15.31 volts. At 1.2 amps power consumption. I'm not sure how much power just my lighted cars take up. 24 seconds. Now it's a different track, so it's not proportional to the other train running, but we can compare it against itself. And as you remember, 2 engines is more better, right? That is the philosophy. So let's stick on our little Japepeo. That's our full consist now. It sounds fast. Looks pretty fast too. 15.31 volts at 1.65 amps. 20 seconds. We shaved off like 4 seconds adding another engine. And that inductor is not even getting warm. Well, that's flippin' sweet. Before, adding the second engine slowed things down. Now it's actually speeding it up. Not by much of a margin. Granted, that consist can use 2 engines for overall smoother transitions from slow to fast. But yeah, I think we're done here. Train box is upgraded. 3 amp beast capable of delivering up to 50 watts of power, which doesn't seem like much, but it's not insignificant for a train set. But whatever, now I don't have to worry about it anymore, and it's ready for Project Ouroboros. I can start building some long trains, not that I haven't already. Not sure if I'm making videos about that, because, well, my videos are technical, so it's when I'm actually tinkering on the electronics or the mechanics that I make videos. I have 100 cars. I have a whole lot of engines. I got more cars coming. I'm just gonna try to pull them all at once, and now I have the power to do that. So I hope you enjoyed this. If you did, stay tuned, because I have some other little bits of train tinkery to do, and yeah. Perfect timing. I just got the battery low warning on my recorder.